Hello everybody, I hope you're as excited as I am. We're going to finish off the 2004 Fermat paper. We got question 25, and then that's all she wrote. Okay? So, if you want to copy the contest, as usual, click the link in the description. I recommend you try the contest questions before you watch these videos, yada yada yada, but let's get into it. Alright, question 25. A steel cube has edges of length 3 centimeters, and a cone has diameter of 8 centimeters and a height of 24 centimeters. Okay. The cube is placed in the cone so that one of its interior diagonals coincides with the axis of the cone, so the middle line right down through it. What is the diameter in centimeters between the vertex of the cone and the closest vertex of the cube? Okay. So, I'm tempted to reproduce this picture because I'm sure we're going to have to mark it up in a little bit. But it's a two-dimensional picture, and they are clearly describing a three-dimensional situation. And that, I know, can be an Achilles heel for some people. A couple of the mathematicians I know, these sorts of problems are not their strong point. Heck, it's not really my strong point either. But, you know, over the years, if one thing you can do, if you know there's a particular type of question you don't like the 3D picture questions. If you know, oh, geez, I hate those questions where they just give you some sort of nebulous function or logarithm questions. If you can identify that weakness, that's a great thing to know, because then you can read up on those things. You can take a look at other problems, get your hands on just about as many problems that you're of the type that you're bad at, try them, look at the solutions, see what's going on, notice patterns in the techniques that they use, and then suddenly they're not so bad for you anymore. Okay? It's one of the best things about practicing these contests is you can quite easily identify your weaknesses, as opposed to, say, just watching the video and saying, oh, you know, I would have done that, yo, that makes sense. Then if you're not trying it for yourself, you don't actually know exactly where you're going to get stuck and what you're thinking about when you're getting stuck. And so that can be a detriment when you actually go out and try these contests for real. If you haven't identified your weaknesses, if you haven't practiced to eliminate your weaknesses, then you can very easily get, you know, 2 questions on the part C that are the geometry ones that you just hate, the circle geometry, that, oh, I just can't do those. So, identify your weaknesses and do your best to eliminate them by getting your hands on as many problems as you can. I know that the instinct is always shy away from these problems because I don't like them, but you're never going to get any better unless you start exposing yourself to them. Okay? So, as I say, 2D picture, 3D situation, that can be a bit of a problem. I did see this question coming, because, you know, I do take a gander at them. I occasionally scroll down. So actually, what I thought I'd do is I'd show you, I just have some household things here, a really, really tiny Rubik's Cube and just a sheet of paper, and I can at least try and make a 3D representation of this to better aid myself. So what I'm doing is I'm just sort of making a cone like that. It doesn't have to be super exact because, you know, it's for my purposes. It's just, can this give me a little more understanding than a 2D picture? And I will plop this guy in. He's not going to sit exactly the way I want. Now, looking at that, I can sort of see he's on the diagonal. And I hope, oh, he's going to shift if I try and show you guys, but see if we can very, very delicately take a look there. I hope that's on camera angle. But, you know, just being able, not for the folks at home, but for me being able to see it, it might shed some new light on something and say, oh, okay. And one thing I do notice is that I'm looking down here, and if you're looking down at a cone, you're going to see it's basically just a circle. And I'm noticing certain vertices are actually touching the edges, and certain vertices look close, but they're not quite touching the edges. And I think we're going to have 3 vertices touching the circle. So we'll put the cone away, because it might even, the question says that it's being held so that one of the diagonals coincides. So it's being sort of held like this in place. And I can see if I hold it like that, that 1, 2, and 3 of these vertices are all sort of at the same height, and then 1, 2, 3 are at another height. So it's going to plop in there and get sort of wedged. Where's it going to get wedged? Where it's the widest and that's at these 3 points. And I think that'll help if we sort of cut a slice across. You get a circle, and a circle will have a triangle. It'll probably be equilateral just because it's a cube, but we'll get a triangle between these points, and that might in some way help us because then maybe we can relate some part of the cone to some part of the cube and get something going on like that. But I wanted to show you can just sort of cobble together these things. You don't have to use tiny Rubik's Cubes. You can actually go out to craft stores and buy just little cubes and things like that. But a piece of paper, a great way to improvise a cone should you need it. Now, some of you out there might just be masters of 3-dimensional pictures. You don't need that sort of help, but that can help. That can help. And so if you're the sort of person who struggles with these questions, see what you can do with household props just while you're trying these questions at home even. Okay? But let's get back into it. I didn't even finish my picture. I did not even finish my picture. I went on a rant about how I'm not the best at these types of questions. So, it's hard even to draw what's going on here. No, this is terrible. Terrible, terrible, terrible. Okay. So we're going to have the top part of my cube and the bottom part of my cube. And now, just holding up my diagram again, just so I can even draw this properly. Okay, I think I can do this. So I have these guys pop out here. They form a square, but it doesn't go all the way to the top because then it goes up a bit. And then we have these higher up fellas. And back here, a little something like, oh no, we want that. And there we go. Not so bad, and the little Rubik's Cube even helped me visualize that. Okay. So that's what we've got going on. That's our picture. And as you can see, we do have this guy back here. He doesn't look like it, but that's because he can't really draw the background of the cone. But we have these 3, and they all sort of lie, they all touch the cone. And they all lie at the same height. I think that's going to be important because I think, if we connect them up, we're going to have an equilateral triangle because each side is going to be a diagonal of a face of the cube. Okay. So I think that's some important information. Now, I have completely forgotten what the actual question is. Determine the distance in centimeters between the vertex of the cone and the closest vertex of the cube. So what we ultimately want is the distance from the vertex here. We want this sort of vertical distance here. Okay. What to do? I want to use this red triangle in some way because we're going to sort of get, I think, dark blue circle. And I think from the equilateral triangle, we could probably figure out the radius. And since we know the ratio between the radius of the cone is 4, and the height is 24. If we knew the radius of this small circle, then we would know the sort of total. We'd be able to, using the ratio of 4 to 24, we'd be able to get the height from the circle to the vertex. And I think because we got this triangle inside the cube, maybe we can get the distance from the triangle to the vertex we want and take the difference. That's my current strategy. I think it moves through logically. I planned it out. And I'm trying to think, is there anything else I could do just by looking at the picture here? And there's not a whole lot of information to go with because there's not a whole lot of interaction between the cone and the cube. Right? We have, heck, even the vertex of the cone and the vertex of the cube we're working with don't really relate to one another. The only point of contact, the only point of reference is the fact that 3 of these vertices happen to hit the cone. So we've got to start with that, and I think my strategy there will work just fine. Okay, so I think it'll work. Now it's time to just put it into practice. So we're going to get some numbers here and try and work with that. So we have the dimensions of the cone. Do we have the dimensions of the cube? Surely we do. Yeah, cube has dimensions of 3 centimeters. All right, so enough messing about with that picture. Now let's take a look. A top-down view of what I've got. We look down here, and the middle of the cone, that happens to coincide with the diagonal of the cube. And then we have sort of these 3 points of contact with the cube. And it forms an equilateral triangle. And these lengths here are diagonals of faces of the cube. And since the cube has side lengths 3, very quickly we're going to get that this is 3 root 2. So these side lengths here are all 3 root 2. And my next plan was get the radius of the circle here. So how the heck am I supposed to do that? I'm pretty sure there's a relationship because it's an equilateral triangle. I just can't for the life of me figure it out right now. I'll tell you what, we'll connect these up here, and because it's an equilateral triangle, this is going to have to be 60, because it's going to be 60 everywhere. Or not 60, 120. 60 for the corners, and the corners are being split in half. So we have 30s here, 30s here, we've got 120s here. And we know this is 3 root 2, and then we've got R and R. I want this radius. At least I think I do. What's the best way to get it? I suppose we could probably use something like sine law, but you know what I'm going to do? I'm going to chop this in half. We're going to get 60, we're going to get 30. R, we're going to get 3 halves root 2 instead of 3 root 2 because we cut them in half. And because it's a chord, a line from the center can cut it in half and give a right angle there. Also, you could just say it's because of an isosceles triangle. But now we have a 30, 60, 90 triangle. And so 30, 60, 90 triangles always look like 1 to root 3 to 2. Those are always the ratios of the sides. This is a useful thing to know. So opposite the 60, we have 3 halves root 2. So R is going to be 2 over root 3 times this amount. Yes. Okay. So the 2's will cancel out, and then we'll have 3 root 2 over root 3. I think I'm going to simplify that just to root 6. Okay. What to do now? So what was the next part of the plan? So we know that the cone is 4. That's a terrible picture. It's 4 to 24 in terms of the ratio of radius to height. I now have the radius of this. I now have the radius of this smaller circle. It's root 6, which isn't the happiest number in the world. But we multiply by 6, so we've got to have here 6 root 6. All right, we take the radius, multiply it by 6 to get the corresponding height. So we had a radius of root 6. We multiply it by 6 and get the corresponding height. Okay. Out of curiosity, is this root 6 ever going to go away? And we take a look at the answers, not so much. But I am actually emboldened by the fact that we've got some 6 root 6s in some of the answers. In fact, E is 6 root 6. And if it had taken you a while to make this connection of, this cut circle with the 3 corners, you might, after a long time, this has happened to me a lot, you do a lengthy computation after a lengthy mental exercise to get yourself in a good position. And then you say, finally got the number that I was looking for, that must be the answer, and you move on. It doesn't happen so much with question 25, because you're sort of at the end of the contest, so you're not sort of rushing to do more things, because usually this is the question you save till the end. But it's entirely possible that somebody could have said, finally get that height, 6 root 6. That was totally the distance from the circle to the vertex of the cone. Wasn't that what we asked for? Okay, I'll circle in E. Okay, you might say, how could somebody be so silly? It happens more often than you think, and it can certainly happen in the heat of the moment when you're worrying about a million things on this contest. Okay, you only have an hour. There's a serious time crunch. But the fact that we've got these 6 root 6s, certainly in the potential answers, makes me feel pretty good. I'm going to guess it's one of A or C, because we still have a bit more to subtract. But, it could be something really far out there like B or something. I don't know. I don't think it'll be D, though. But, 6 root 6 in 3 of the answers, that's looking good. I like that. So, any doubts I might have had sort of melt away at this point. Okay, so 6 root 6 is the height. So we're going to do 6 root 6 minus a little something. All right, because we have this, let's see if we can draw a bit more of it. We have this cube, and we've got a little extra bit. Because a bit of the cube is hanging down below this circle. So I need to figure out sort of how much of the cube is below this circle. And I'm trying to think how to do that. I think drawing a picture and maybe not considering it below the circle, maybe considering it above the circle might be a little bit better. So now I'm going to sort of flip everything. So now here's my circle. I'm going to draw a big picture because I really want to sort of understand what's going on here. And then we have our 3 points. And they each, and we've got, I'm going to use some colors here. We've got the 3 root 2 here. 3 root 2 here, 3 root 2 here. And so these are sort of isosceles triangles, half of squares basically, jutting out, and they all meet at this point here. And I want to figure out how far above the circle is he. Well, fortunately, he lies exactly above this center dot. Is there anything else I can add here? Yes, I could add the radius is root 6. We worked that out. Okay. So, if he's sitting right above, then surely we have some right angles here. And then this side length is 3. This base is root 6. And the height is what I want. And I have a right angle triangle right here. So that's actually, I think, is about to solve it quite quickly right now. 3 root 6 h. So by Pythagoras, 3 squared minus, or is equal to h squared minus root 6 squared, and that root 6 actually isn't a bit of a burden right now because it's just going to be 6. So 3 is equal to h squared. H is going to be the square root of 3. And that was the distance left that I needed to make up, so distance between the two vertices, the vertex of the cone and the vertex of the cube that's closest, is that total distance between the circle and the vertex of the cone. minus this height that is the distance from the vertex of the cube to the circle. And I don't think I can simplify that, and I think this was one of the answers. Was it C? No, but it was A. So I'm really confident in that. Things sort of fell into place there. I liked that one. It wasn't as bad as I thought it would be, considering, you know, the geometry, a 3D geometry problem, and I do have some issues with that. Yeah, I think sort of once I realized that, that those three vertices all happen to lie at the same height, and I could quite quickly see that with my props. So, you know, yay for props. But once I made that connection, they had to, since they're the lowest ones and they're sort of the widest looking down, they're as wide as the top ones, but the top ones will be higher up and won't be hitting. Once I realized these three bottom cones all hit bottom points all hit the cone, and so they sort of lie at the same level, realizing that's sort of the only interaction between the cube and the cone, you have to go from there. And what to do, well, sort of, if they're all at the same height, you can sort of slice the cone. From there, you get equilateral triangle, you get radius, so you get a ratio of the heights, and then you say, oh, okay, how far down is this little bottom one from these three, and take the difference. That's actually quite smooth. Okay. So I think that's a good way to end the competition. Hopefully you guys enjoyed it. Yeah, if you had another way of doing this, I'd love to if you left a comment about it, because I really think this is sort of the only thing you can do. Because these points here are the only interaction between the cone and the cube, so that's the only thing you can build on. Anyway, so that does it for the Fermat. That's the multiple choice grade 11 competition. If you want any other of the CMC's competitions, Gauss's, Galois, that sort of thing, click the second link in the description, and you can go to their website and you can try any of their competitions. They also have answers, and I think they do post rankings, although that won't be so useful to everyone. I mean, seeing what schools did well in 2004 is not going to help you right now, but I think they do have that information. Anyway, the next thing I'm going to do is the Hypatia, which is still the grade 11 competition, but now it's written answers as opposed to just get your multiple choice. You know, if you can narrow things down, that sort of thing. So it's a different bit of a beast there, and it's better preparation for things like the Euclid, which is the scholarship paper. So 2004 Hypatia is what's up next, but if you're looking for more Fermats, I do have the 2003 you can go look at some point in the future, the 2005. Okay, so have a wonderful day. Thank you guys for watching, and I'll see you with whatever math contest you're watching next.